The natural exponential function has to do with the number e. And the decimal approximation of e is 2.71828182846, and it is irrational, so there's no pattern. It is like pi, similarly, that it's got a decimal approximation. The decimal approximation that we're going to go out to is 3 decimal places. It's approximately 2.718. Now, where that decimal approximation comes from, where does the value e come from? If you were to find the limit as x approaches 0 of 1 plus x raised to the 1 over x, you would find that that function, 1 plus x raised to the 1 over x, looks something like that, and you would have 0, e. So as x approaches 0, from the left-hand side, you'd be approaching e. From the right-hand side of 0, you'd be approaching e. That's what that is equal to. That is what that is equal to. That limit equals e, and that's where e comes from. Another way to write it is the limit as x approaches infinity. Now it's a horizontal asymptote. 1 plus 1 over x raised to the x power. This looks very familiar. If you think about our compound interest that we've learned in the past, that function, 1 plus 1 over x raised to the x power, that right there is very, very familiar when it comes to our PERT, when it comes to our compounded continuously, but compounded n times 1 plus, we can prove it. And maybe I'll do that in another video where I'll prove it. It equals e. We want to start by sketching y equals e to the x. This is a parent function. And I'm going to start by making a table. When I put negative 2 into this function, e to the negative 2 is about 0.135. You can find e on your calculator by hitting the second key, or it might be a shift key, and then LN. So the second key and then the LN key. And that should give you e, and then it should be asking you for an exponent, and you can just put the first power in. That would give you 2.718. In this case, we're going to put a negative 2 in for the power, which is going to give us 0.135. Negative 1 gives us 0.368. Putting a 0 in, we get a 1 out. Putting a 1 in, we get 2.718. And putting a 2 in, we get about 7.389. So when we put a negative 2 in, we get about about a tenth. We'll just call it that. When we put a 1 in, we get about 4/10. When we put a 0 in, we get a 1. When we put a 1 in, we get between 2 and 3 at 2.7-ish. And when we put a 2 in, we get out between 7 and 8, which is 7.4-ish. And this is no different than y equals 2 to the x or y equals 3 to the x. It actually happens to be sitting right in between the two. So if I were to graph y equals 2 to the x, it would look very similar to this. Y equals 3 to the x would look very similar. And this curve would be sitting in between those two. Now you try with a reflection, y equals e to the negative x. So see if you can graph this function with a reflection over the y-axis. And if you're back, you put in a -2 and got out between 7 and 8. You put in a -1 and you got out 2.7-ish. You put a 0 in and you got a 1 out. Put a 1 in and you got about 4/10 and then about 1/10. And hopefully you saw that your graph is decreasing from left to right with a horizontal asymptote at y equals 0. So our graph that we've had as an example is increasing. So I'm going to try and recall some information that you may or may not recall from college algebra. This graph is increasing while this trie is a decreasing function. It's decreasing all the way. We can also talk about the concavity. The one that is increasing is concave up, and the one that is decreasing is concave down. Now, exponential graphs look like this. That's what an exponential graph looks like. You've got maybe time and then population. So when we're talking about maybe the spread of the flu or the spread, we could take chunks of data for the spread of COVID-19, and there were certain chunks in time where we had some exponential growth, and that could be modeled by an exponential function. We also have what's called a logistic function. Now, what's interesting about a logistic function is that you've got this going on, and it looks exponential, and then right here it's got a point of inflection where it turns towards concave down, which is more logarithmic. So we use logistic functions when the population growth is restricted. So this is used when the population growth is restricted. For instance, if we're talking about the football team, let's say that we have a few cases of the flu. We have a few cases of the flu, and flu is contagious. We know that every year there's a flu season, and let's just pretend that nobody on the football team got a flu shot. If we were to group the football team and quarantine them together, knowing that 1 or 2 people had the flu, what would happen is eventually the whole football team would get the flu, or pretty much close to thereof. So it wouldn't continue to grow exponentially. So you couldn't grow exponentially because you have a limit to your population. So this limit might be the number of football players on the team. So the number of football players on the team, that would be the limit as to how many people would actually finally get the flu. So what would happen initially is 1 or 2 people have the flu, right? And then they give it, and then they give it, and look at that. It grows exponentially. But now there's not as many people to catch it. So now that growth starts slowing. And look at this. Because we are in calculus, look, we've got our first derivative is increasing, and then what's happening? Our first derivative is decreasing, right? So the rate is slowing. The rate of change is slowing. Let's talk about bacteria culture. It's growing according to this equation, y equals 1.25 over 1 plus 0.25 e raised to the -0.4 t power, where t is greater than or equal to 0. So this model right here is our logistic model. So I'm going to highlight that so I don't have to rewrite the whole thing. This is a logistic model. So I'm color coding. Y is equal to the culture weight in grams and T is equal to the time in hours from the initial weight. So this culture is growing over the course of several hours. Find the weight at 0 hours, 1 hour, and 10 hours. 0 hours, 1 hour, and 10 hour. So what you're going to do is you're going to put 0 in for T, you're going to put 1 in for T, and then you're going to put 10 in for T. Go ahead and press pause and practice using this equation with your calculator. There's several different ways that you can do this. You can flat out just put it in straight into your calculator and re-enter this over and over and over again. Or you can put this into your Y1 and then use the table feature of your calculator. However you feel most comfortable using your calculator, but make sure that you press pause and then come back and check your answer to make sure that you've got it. Okay, welcome back. If you have not paused this video, you've done yourself a disservice. Please make sure that you know how to put this into your calculator. 1 gram when we have 0 hours, 1.071 grams at 1 hour, and 10 hours we have 1.244 grams. What is the limit of the model as T increases without bound? What is the limit? So the limit as T approaches infinity, that's without bound, of our function 1.25 over 1 plus 0.25 times e to the negative 0.4 t power. What is this going to equal? As t gets bigger and bigger and bigger, this term is going to be closer and closer to 0. It's going to become insignificant. The reason being is because of that negative 0.4. So a negative times a really big number is a negative big number. E to the negative large number is going to be 1 over e to a large number. 1 over a really big number is like 0. It becomes insignificant. And 0 times 0.25 would be 0. So all you would be left with, this is going to become closer and closer to 0 as x gets closer and closer to infinity. So we'd have 1.25 over 1, which is just 1.25. Now, according to this model, will the weight reach 1.5 grams? No, it's never going to reach 1.5 grams because that's outside of its restricted growth value. And the growth value is going to go up to only 1.25. So this 1.25 ends up being this value right here, this asymptote, that's your population restriction. That right there ends up being as high as we are going to be able to go growth-wise. Therefore, no. The weight's going to approach, so it will approach 1.25 grams, but never get there, and it's never going to exceed it. Now, eventually, for all intents and purposes, we're going to say it's 1.25 grams, because in the real world, 1.2499999999999 is 1.25. So there's a little bit of review with graphs. I know that the logistic graph was new, but hopefully it makes a little bit of sense, especially with that concavity, your point of inflection, the horizontal asymptote being the numerator. That's your limit. That's your population limit, or in this case, your growth limit. And we'll come back in the next video and we're going to work with financial models.